As July temperatures soar to record highs in 2026, London's masonry is becoming a silent killer. This investigation examines how solid brick walls, lacking the natural transpiration of permaculture buffers, interact with extreme heat to create life-threatening indoor environments. 19th century builders designed these heavy masonry structures for a specific climate. In an era where surviving cold, damp winters was the priority, solid brick walls were constructed to capture and hold every bit of warmth generated by indoor coal fires. That design logic relied on a climate that no longer exists. Between 2012 and 2021, London's average temperature was 1.0 degrees Celsius warmer than the 1961-1990 baseline. The historical need to retain heat has become a liability during modern extreme heat waves. The architecture is performing exactly as it was designed to, but in an environment it wasn't built to handle. The physical mass that made London's historical buildings so resilient against the cold is now the primary source of their vulnerability. To find the source of the problem, we have to look at the primary building material defining the city, the solid Victorian brick wall. When we analyze the physical properties of the South Lambeth stock brick, we begin to see how the masonry responds to thermal stress. This material has a dry density of 1,810 kilograms per cubic meter. That density results in a thermal conductivity of 0.593 watts per meter Kelvin. This chart shows the U value, the rate of heat transfer. Standard models assume an uninsulated solid wall transfers 1.7 watts per square meter Kelvin. However, laboratory testing reveals an average rate of 2.1, with some reaching 2.6. These walls gain heat much faster than predicted. This high conductivity allows the dense clay to act as a thermal sponge. The walls rapidly absorb solar radiation, storing energy deep within the masonry. Because of this U-value miscalculation, London's historic homes are effectively charging up like massive heat batteries every summer afternoon. To improve energy efficiency, many of these buildings have been retrofitted with modern seals, double glazing, and draft-proofing to retain heat during the winter. But those same airtight seals have eliminated the natural nighttime ventilation pathways that these Victorian houses originally relied on to shed heat. By trapping that stored energy inside with no way to circulate air, these retrofits have inadvertently turned living spaces into sealed containers of heat. This results in thermal lag. The bricks hold their charge for hours, only beginning to release that stored energy long after the sun is set. By 2 a.m., the walls can radiate 30 degrees Celsius heat directly into a bedroom. The interior can actually be warmer than the peak temperature of the day. Electric fans are ineffective here. They only circulate the existing hot air and cannot counteract the massive radiant heat coming off the solid masonry. When the environment stays this hot, the human body cannot shed its own internal heat, preventing deep sleep and causing continuous cardiovascular stress. This is where the risk of heat exhaustion and heat stroke peaks. Once a person's core temperature is forced past 40.6 degrees Celsius, the condition can become fatal. The 24-hour cycle of thermal charging and midnight radiation has transformed historical infrastructure into a physical trap. To break this cycle, architects are looking at permaculture buffers, living skins that provide an active biological layer on building exteriors. This introduces evapotranspirational cooling. Leaf stomata intercept solar radiation, using that energy to evaporate water before the heat can ever reach the brickwork.
This phase change converts solar energy into harmless latent heat in the air, rather than storing it as sensible temperature in the building's fabric. It is a self-regulating biological system that stands in direct contrast to the passive, heat-absorbing physics of bare masonry. While foliage coverage is important, the specific taxonomy of the plants used determines the ultimate cooling capacity of the wall. A single layer of Heuchera micrantha palace purple keeps a wall at 24 degrees Celsius against a 45-degree bare surface, a 21-degree differential. Alchemilla yields similar results, dropping temperatures 19 degrees and boosting relative humidity to 52%. These supercoolers can be integrated into existing buildings through modular living walls or simple wire trellis systems. Shifting from hard, heat-absorbing surfaces to active biological ecosystems is the most effective way to neutralize the thermal mag inherent in London's brick housing.
Subscribe to TEMBODocs for more investigations into the intersection of climate, physics, and the built environment. Click the bell to stay updated on our next report.